Okay, exponential graphs. Now, with the exponential graphs, basically we're also throwing in exponential equations, exponential functions. So it's basically all those things, and we'll look at each different little aspect of what we're looking at exponentials. That's the big thing we're looking at today. Okay, the big thing that we have is that we're basically kind of transitioning away from some of the things we've done before and making some things a little bit different now. That, and you don't have to write this down, just kind of give you a visual here. In the past, with a lot of the graphs we've been doing x squared, x to the third, x to the fourth, x to the fifth, doing a lot of the different, factoring and graphing and solving and doing all kinds of things with, x to a certain power. When we're doing exponentials, the basic shape, the basic idea that we're looking at is now just the opposite. That now you're going to have a number for the base, and x is going to be in the exponent. So the basic form of the equation is y equals b to the x. If you want to think about just a number with actual numbers on this thing, is that now you're looking at something like this, where y is equal to the x power. If you put it in terms of functions, again, the big difference is that you replace the y with f of x. So it could be that you got something like that. So that's the difference. That's what we're basically looking at for exponentials on these. All right, and some of this is going to, some of the problems, very beginning ones, just going to make sure everybody's okay plugging in values into exponential functions or exponential equations. And again, same thing, just how they're noted in that point. But again, the big difference is we're looking at that x is now in the exponent. Okay, so what we're going to do is we're going to do one example and just show you the basic shape of a graph that's an exponential function and talk about everything that's kind of similar to it. I don't think you'll have to do this a lot, but there may be one or two questions in the homework that you'll do. Now, test-wise, you will not have to do this first example like we're going to do, because we're going to, after we got the basics on it, everybody's good with it, we're going to kind of move, just like when we were graphing x squared. The first time we did it, we plotted 7 or 8 points just so you could see the shape of it. We'll do the same thing with exponential. We'll plot it one time so you can see the shape of it. And then after that, we're not going to plug in 7, 8, 9 points. We're going to be able to just look at it and go, oh, it's this graph, and we're going to move it up, down, left, right, and we're going to put it here, kind of thing. So it's just making sure that everybody kind of gets through this first step of knowing what we're going to do for this thing. All right, so let's say we're going to graph, and we'll do y equals so we get x and y values, which makes it easier to graph. Let's start with one of the easiest exponential functions that we'll do, which is like y equals 2dx. All right, and somebody may be asking, well, why don't we do 1 to the x power? Wouldn't that be an easier exponential function? No, because what's 1 to any power? It's always 1, right? So if you graph y equals 1 to the x power, it's not going to be anything other than just a bunch of 1s. So that part's a trick question. So the base has to be something other than 1 is really what it comes down to for this thing. So, all right, so over on the side, let's make a little chart over here. So for x values, we'll go from positive 3 down to negative 3. Our equation is y equals 2 to the x. And at the end over here, we'll put our x and y for our order pairs. Okay, so putting this one off to the side, and then we'll come back and graph it back over here once we get finished with it. Okay, so we start with 2 to the third power. What is 2 times 2 times 2?
8.
Okay, so y value is 8. So if we do order pair on that one, it'd be 3, 8. All right, what about 2 squared? 2 times 2 is 4. There we go. No trick questions so far. To the first power, 2. There we go. Ooh, now here's the great question. And we've talked about this before. See if anybody remembers. What is 2 to the 0 power?
0.
Yeah,
Why would it be?
I'm not gonna
It is
lie.
1. Okay, so again, we talked about, just go back and remember that if you take away a power of 2, so we got 2 to the third, 2 to the second, 2 to the first. Every time you come down a power of 2, you're dividing by 2, right?
Yeah. Okay.
So if you keep dividing by 2, 2 divided by 2 makes it out to be a 1.
Well, how come it wouldn't be 0?
So if it was 0, which is a good question, let's just pretend for a minute 2 to 0 was 0. All right. So if you're okay that if we came down a power, we divided by 2. If we move up a power, we need to multiply by 2, right? So what's 0 times 2?
Oh, 0.
0. And if you do another power, 2 squared is then 0. So
Oh, so it couldn't be 0. Because
correct,
then
yeah.
everything was 0.
There you go.
Okay.
Okay. Now for that one, again, we've talked about the negative exponents just a little bit.
Could you say could you see whatever are you dividing by 2 because of your b value being 2?
Yes, because your b values 2. Yeah.
So could you say you could solve the first 2 and then go down the line just dividing the product by 2?
Yeah.
And it would always be the same.
Yeah. So if we keep going down the list on this one, if we need to get to -1, so if we do 2 to the -1 power, the answer we're going to get is we're still going to take this previous answer here, and we're still going to divide it by 2, which means that answer is going to be just 1/2.
Oh, and then you just keep going?
And then if you want to keep on going, you can just keep on going. You just keep dividing by 2. So if we do 2 to the -2 power, all right, now here's a good question on that one. What is 1/2
Quarter.
divided by 2?
Quarter.
Yeah, keep it, change it, flip it, right? That's basically 2 over 1. So that's 1/2 times 1/2, which would be a quarter, which would be a 4. All right, now here's the great thing with the exponents. Here's the connection you can kind of get. The only difference between 2 squared and 2 to the -2 power, this answer is 4. This answer is 1 over 4. So the only difference, and that's, again, something we did with negatives a little while back, but you may have kind of glossed over a little bit. The only difference between a positive exponent and negative exponent is if you've got 2 to the first power, it was 2. If it's 2 to the negative first power, it's 1 over that answer. So you can take whatever this answer is and just put 1 over. So if we know that x to the third is 8, we know that this answer is going to be 1 over 8. But again, you can still get that same answer by dividing it by 2 to get there.
What would you put in the x, y with the fractions?
Okay, so with the fractions, yeah, and that's going to be where it's not so much fun. You can go ahead and put the 1/2 if you want to. If you want to put 0.5, you can do that. Either way's fine.
So how come it's 0?
Oh, sorry. Should have been -1. My bad. Thank you. Good catch. All right, so that was -1. That's -2. If that's a quarter, that's 0.25. That's supposed to be a negative. Yeah, I messed up there.
Oh, negative. Okay.
Yeah, -1, -2. If you don't have a pencil, make sure you got some correction tape close by.
Oh, that's so nice.
There we go. Now we got it fixed. Question.
All right. So could you say unless your b value is negative, then you'll never have a negative y?
If it's just a number to a base, then yeah, we actually will have a couple of different things we'll talk about. That if your base is greater than 1, this is the way to look, and if your base is less than 1, then we got a different way to look. So we'll kind of break it up into parts. Yeah.
She's learning to ask questions. No, I just actually understand to ask questions.
Okay, and if you're not, again, with the decimals, you can either put these answers as decimals or fractions. It really doesn't matter how you write those answers. They probably will let you leave it in fraction form, if I had to guess on some of those. So we'll be good. All right, so graph-wise, here we go. When we go to graph these,
Is it gonna be a line or is it gonna be like the positive and negative you just did?
It should actually be a curve when we get finished with it. So.
A curved one.
Okay, so get your XY axis, and again, just so it fits on here, we've got to go to at least 8 to get this value. So I just made the Y axis a little bit smaller so we can make sure we fit it in. Okay, so then we're just going to plot our points. So at 3, 8, that would put us up here. At 2, 4, that would put you right there. At 1, 2, that would put us here. 0, 1 would put us here. Now, and the rest of these, once you get to the decimals, you're not going to have to plot decimals because it's going to be, I wouldn't say impossible, but it's going to be extremely hard to get a very accurate plot on that one because you'd have to have so many like tick marks in between these either. So from there, we're pretty much kind of guessing with these. -1's about a half. -2 is about a quarter. -3 is 1/8, and it's going to be so hard to tell at that point that basically it's going to be sitting like right on top of 0. So if we connect your points, you're going to get something like that.
It's so cute.
Yeah, so it's a nice little curve. You can almost think about this one. It's almost like a plane that takes off in a hurry. If you've ever listened to any of the military pilots, they talk about if they're trying to take off in a plane in basically an active war zone. Most of the time, if you're in a passenger commercial plane, you take off, and then once you get lifted up, you just have this kind of nice, smooth. You gotta go easy. A lot of times, you'll hear, especially if it's in Air Force One and they're in some hostile territory where they're going, they don't just kind of ease up. They take off and they get up out of the sky in a hurry. So a lot of times they'll take off, and then instead of just easing up, they get up as fast as they can to try to get out of the airspace that they're in. So that's what we'll do in this one. So now, and that's the basic graph that you get for your exponential function for this thing. And the only difference is that if this base is different, if this base had been 3 to the x power, the graph is going to look exactly the same. It's just this graph is going to get a little bit steeper if it's 3 to the x power. If it was 4 to the x power, it would be just a little bit steeper than that. If it was 5 to the x power, it'd be just a little bit steeper than that. If it was 6 to the x power. So basically, the bigger the number, the faster this line is going to go up. You can almost think about it's not slope, but it's similar to slope that if it's a bigger number slope, it should have a faster rise as it's going through that part. Mm-hmm. So they're all going to basically fall into this same category, that they're all going to have this same basic shape at some point in form or another.
I do have a question.
Sure.
If the base number is negative, would it be on the other side?
All right, and the base number is negative, it's going to flip the graph around, yeah.
Okay.
So here's kind of where we're going with this one. If everybody's okay with that graph. Now here's the thing. What happened here? What's the one point that's the same for every single one of these graphs, no matter what this base would be?
1.
Yeah. If you plug in 0 for x, if it's 2 to the 0 power, it's going to be 1, right? If it's 3 to the 0 power, it's going to be 1. If it's 4 to the 0 power, it's going to be 1. If it's 5 to the 0 power, it's going to be 1. So our new reference point for this one is 0, 1. That all the other graphs we've done up to this point, we will always go back to 0, 0, and we'd start at 0, 0, and then the graph would change from there. Okay, exponential is because of the way it works. If you plug in 0 to a basic exponential graph, then you're always going to get 1 for the answer. So everything we're doing from now, you got to think that 0, 1 is like our new reference point. That instead of everything going back to 0, 0, everything is going to go back to 0, 1, and that's going to be our reference point of where we're going to move up, down, left, right when we get there. All right, so
on the test, are we going to have to sketch the graph?
You will have to just sketch the graph, just like when we were doing x squared, how you just had to kind of sketch the graph on that one. But same thing with that one. We look for like one or two key points. Same thing for these. We're going to look for 1 or 2 key points, and then you won't have to plot all these other points, because again, these points, there's no way to make these points accurate because the numbers are so small. So we're just going to find one or two key points, and everything else will be okay. Okay. Okay, so here's what we're looking at. And here's kind of our two cases. If you're doing y equals b to the x, which is our basic, exponential thing that we're looking at. If the base is greater than 1, then this is how the graph is going to look every single time. This is going to be your basic shape every time. Okay, and if you're doing this one, if your base is greater than 1, they're going to call this thing exponential growth. And it's not really the exponential that's the key word. In this case, it's the growth. That's the key thing.
Would it be exponential decline if it was the next
Um, well, yeah, instead of decline, they call it decay, but same thing, yeah. Okay. So think about, for anybody that's taken science classes, what happens when you get just a little bit of mold?
one? A little bit of what?
You get some mold, you get some bacteria growing. What happens when you just let that bacteria sit there? It's going to grow, right? And then it's just going to keep growing. It's going to keep growing. So that's your exponential growth. If you start off with just a little bit of bacteria, especially if you get the right environment where it's just the right moisture, just the right amount of heat and temperature, that mold can just take off and grow. So that's kind of what we're looking at for this thing. All right, we are going to talk about domain and range on this a little bit. All right, domain and range. Domain's going to be easy. Domain is going to be negative infinity to infinity. Okay, for the range, if you notice this graph is, and again, y of a's, we get really close to 0, but you never quite get there. There's always still some small trace amount that's there. So for a range, we're going to go from 0 to infinity. Or again, you could say that y is greater than 0. You can kind of go back and forth on those two things. All right, now here's where we get to borrow just a little bit from the last section we did with all of our asymptotes and all the different stuff that's here. There is going to be an asymptote.
Oh.
Okay, so you are going to have an asymptote right on top of the x-axis. So you've got a horizontal asymptote at y equals 0. So that's why we did a little bit with the asymptotes last time, because again, we need to talk about that before we talked about exponential graphs, because we're bringing back in the asymptotes. And again, this is a fence. Now, the difference is on this one, there is no gaps in the fence. There is no gates on this one. This is a hard line. You do not cross this line for exponentials. That is a definite cutoff line. You are not going to get to that point. When we're doing all the rational function stuff, we talked about that there could be a hole in the asymptotes or a hole in the graph that goes through the asymptote that allows you to cross over. For everything exponential, that's a hard cutoff line. You're not going to go below that line, or if the graph was down here, you're not going to go above that line. Okay, and that kind of ties in with your y values here, that y is greater than 0, which means, again, at this point, that's your cutoff line for that thing that we're looking at. Now, if they do happen to ask you, and we've done this before, but just a quick reminder, if they do ask you to find the y-intercept, because that may be one of the key points that you may be asked to find as we're going through these. Remember, to find the y-intercept, all you have to do is you have to plug in x equals 0. Again, that may be one where you would want to use your calculator, because if you plug in the 0 value, most time you can very easily just plug that in on your calculator and you got the answer you're looking for. Okay, so that's our basic graph. So for every exponential, if your base is greater than 1, they're always going to have that same basic shape. and then you have a horizontal asymptote here. Your domain and range will always kind of set up like this one, and we go through that part of it. And all we're going to do in just a little bit is we're going to take this same graph we got, and where we've got this graph that's here, we're going to move it up and down and left and right. But again, the good thing is the asymptote always moves with the graph, so it's the whole thing that moves. So if you've got a graph that's here and your asymptote is here, as you move your graph, the asymptote's going to move with it. It's still just the same graph. We're just going to move it up, down, left, right as it goes through this thing. Okay, so that's our exponential growth. Okay, so if you have growth, you can also have a decline, or what they call exponential decay. And with exponential decay, the big difference on this one, again, it's going to be still the same thing, y equals b to the x, or f of x equals b to the x power. But the big thing is with decay is the base is going to be between 0 and 1. So exponential decay, it's somewhere, because again, you won't use 0, because if you plug in 0, that messes things up. You're not going to, it's just going to be the same answer every single time. We know it's going to be that part. So anything less than 1, basically now we're at a decimal number. So if it's a decimal number, it's not. So you can kind of think about exponential decay. Is it somewhere between 0 and 100%? It's not 100%. We're dealing with less than 100% of this thing. So it's going to wind up being decaying as we go through this one. So your basic graph. Again, we're not going to plug in a bunch of points. Look, something like that. Okay. Again, what's our new reference point?
0, 0. I mean 0.
There you go. So that now, even with exponential decay, it's still going to go through 0, 1, because what happens if it's a half to a 0 power?
What?
If you do a half to 0 power, anything to 0 power is still
1.
1. So no matter what that number is, if it's a number to 0 power, it's still going to just be 1 as we go through this thing.
Okay.
Okay. Your domain and range would still be the same.
Is the main range the same all the time?
Domain will always be negative infinity to infinity. The range will change depending on the numbers that you plug in.
Okay. I can do that.
Yeah, so your domain never changes. The range is the one that's going to change a little bit based on the numbers that you plug in. Yes. So anything to the 0 power it could be 4,765 to the 0 power. It doesn't matter what that base number is. If it's any number to the 0 power, it's going to be 1. Okay. So same thing back here. If this was a half, or a 12th, or 1 over 120, it doesn't matter if it's that number to the 0 power. It's always going to be 1. So even with decay, you're still going to have 0, 1 as a reference point. Okay, so we've got two kinds of graphs. If your base is greater than 1, it looks like this. If your base is somewhere between 0 and 1, it's going to look like that. All right, so here's where we get to move stuff around. We got transformations. More than meets the eye. All right, so here's the transformations. Here's what we're looking at. Now, again, base-wise, it doesn't matter. The base can be anything at all. It's still positive or negative. 0 doesn't matter. The base is still the same. We're going to do a plus c that's in the exponent. So if you add or subtract, a constant. And again, that C is a constant value. If you add or subtract a constant that's inside the exponent. Now, here's where the similarities come back in. I think I may have mentioned this way back when. If we go back to, and just throw this up to you real quick here. What happens if we put a number inside the parentheses?
It goes to everything.
Just moved it 2 spaces, which way?
I don't know.
Horizontally, correct? In the opposite direction. So this would have moved it 2 spaces to the left because it was inside. And if we put a +3 on the outside, that was your vertical movement. That was 3 spaces up, right?
Mm-hmm.
So if it's in the exponent, it's still the same thing. If it's on the inside of the exponent, so if you add or subtract a constant inside the exponent, it moves or transforms or shifts the graph. Everybody want to say that? We're going to go opposite horizontal. Opposite. So it's still the exact same movement. Anything on the inside. Now we just changed it from being, a parentheses. Now we're changing it to the exponent. But if it's on the inside the exponent, it's going to move it opposite horizontally. If you put it on the outside, so it's like that. And again, most of the time you'll be able to see that because this one, it'll be a very small number because it's in the exponent. When it's written like that, it'll be a much bigger number. So it's not, they're not trying to trick you in any way here, this part of it. So it's always, it'll be easy to see the numbers here. So if you add or subtract a number that's on the outside, so if you add or subtract a constant outside of the exponent, it shifts, it moves, however you want to say it here. It's going to move the graph vertically. So inside is opposite horizontal. Anything on the outside, it's vertical. And that's, again, the vertical part's always in your normal direction. Okay. And all the other movements, all the other stuff that we did comes back, and it's still the exact same thing as we talk about all the different parts and pieces on this one. If you put a negative in front of the base, so if you have -2 to the x power. So if we're doing 2 to the x power, if you put the negative in front of the base, so it's like -2 to the x power. That's going to cause or causes a reflection about, around, whatever you want to say there, the x-axis. Because again, in that case, the negative is not in the exponent. It's still outside of the base in that case. So you're going to reflect it across the x-axis, which again, if you do that, that means you're going to reflect it vertically. If it was if you put a negative in the exponent, which I don't think they would ever do that really. If you put a negative in the exponent, that's going to cause it to flip horizontally if you go through that part. All right, and then the last little thing we've got for this one, if you multiply by number, Again, not hashtag, but your pound symbol there. So if we multiply by some number, if that number is greater than 1, just like we did before, it's going to stretch the graph. If your number is less than 1, it compresses the graph.
And multiplying which part, the exponent or
That would be so if you're multiplying that case, so that would be a constant would be out front. So it would be, so it'd be like 2 times x to the 4th power or something like that. So in this case, we're talking about a number that's out here out front. Again, whether you stretch it or compress it, for those of you going into pre-cal, it's still a dilation. So it doesn't matter stretch or compress. They still, and when you get into pre-cal, because they won't talk so much about stretching and compressing, they will a little bit, but it's still just a dilation. They'll talk about a dilation greater than 1, which does stretch the graph, or a dilation that's less than 1, which will compress the graph. Okay, so again, that's a number that's out front. So if you've got your base exponential function you're working with, then the number out front is kind of what we're looking at. All right, so let me do this. So now let's show you a graph that you have to do. But again, we're not going to graph this thing with 45 points. We're going to go, here's just a basic graph. We're going to just take our graph. We know we're going to move it up, down, left, right, just so we got an idea of how this thing would graph. And again, we're not going to plot 8 points, 7, 8, 9 points like we did with this one. We're going to get our basic couple of points we need, and then we're just going to graph everything from there. All right. So let's graph y equals 3 to the x minus 4 power. And we're going to describe how it compares to y equals 3 to the x. Oh, sorry. Get that where y'all can see a little bit better. Okay, and one question they'll probably ask for a lot of the different things that we're going to work through is they may ask you, all right, is this thing a growth or is it a decay?
Can you stop saying like it's just unnecessary. You're fine, you're just
Okay, so very first thing is, and this is the part that we can kind of get, so we're going to graph it, and it says describe how it compares to 3 to the x power. So if we, and again, I'll put this as a dash, so we're going to do 3 to the x as a dash line, just so we can see what's going on. Okay, so that would be 3 to the x power. Okay, so then the question is, if we've got to graph 3 to the x minus 4 power, what does this negative 4 do to this graph? Which way does it move it? It move it forward which way?
To the left. No, to the right.
There you go.
To the right.
So it should be 4 to the right. Yeah, because if you take that part and set it equal to 0, you get x equals 4. So it's a positive number, really. So again, we're moving it 4 spaces to the right. So it's always the opposite direction. Okay, now, on the graph wise, here's all you have to do. Here's what I'm looking for. We know that this point would be our reference point. So what I'm looking for on the graph on this, whether it's on Math Excel or whether y'all graph this on the test and you have to hand graph it, you're going to take this point you've got here that's 0, 1, and you're going to move it over 4 spaces. 1, 2, 3, 4, and you're going to put a point right there. And then all I need to see is that if you move this point over, I just need to see that the graph goes up like that and then comes out and narrows down so it does something like that. And that's all you got to do. That's all I'm going to ask you to show on this thing. Just like when we graphed x squared, we needed a vertex. Well, the vertex in this case is not really a vertex. It's just a reference point we got. So we're going to put this point here, and then we're going to graph it. Question.
I know our reference point is 0, 1.
Mhm.
That's why we have to go through it. But how do you know which way the graph is going? You see how
Oh, and that kind of goes to the next question. So is this a growth or decay graph?
there's a growth going?
So if it's growth, it has to look something like that. If it was,
How do you know it's growth? Like, how do you graph it out?
so anytime it's growth, it always looks like this. If it had been decay, it would have been like this.
This is the same one.
So anytime it's growth, where the base is bigger than 1, it's got to look at graph like that. And that's kind of what we went back to on that last graph back here. So anytime it's growth, it's always going to look like this. Anytime it's decay, it's going to look like that.
Right.
Yeah.
So we're done, huh?
So how do we know it was growth or decay?
Because the way the graph was going.
Right. And we know it's growth or decay based on this number right here. So that's 3. Your base is 3. So your base is bigger than 1.
Mm-hmm.
So your base equals 3. In that case, your base is greater than 1, so we know it's growth.
Okay.
Oh, so come with notes, right?
No, still got a couple more guys.
I have another question.
Sure.
So it's not because it's positive.
Could be tied in that a little bit. But mostly, now we'll still have some that lead positive numbers, but they'll still be decayed. So it really comes down to if your base is greater than 1 or if your base is less than 1. Is really what it comes down to. So
if it's less than
yep. So anything less than 1, it should be decayed. All right. Now they may ask you to possibly to find the y-intercept. Which again, if you got to find the y-intercept, that just means you're going to plug in x equals 0. So we're going to plug in 0 back up here. Again, that's 3 to the 0 minus 4. Well, that's 3 to the negative 4 power. And again, you can do this a couple different ways. If it's 3 to the negative 4 power, you can think that would be 1 over 3 to the 4th power. Because again, we said the only difference between a positive and a negative is if it's negative, we got to write it as 1 over that number. So that could be 1 over 81. Because they probably, in that case, will not ask you to write that as a decimal number. I mean, you could write that as 1 divided by 81 and get that number. But they're probably going to ask you to write that number as a fraction. They may let you write it as a decimal number if they ask for it at all in those parts. So again, that kind of goes back to this thing. If we know it's negative on the exponent, we can just take the answer if we didn't have a negative and write it as 1 over that answer. So if it was 3 to the 4th, 3 to the 4th would be 81. But since it's 3 to the negative 4th, we can just write it as 1 over 81.
What did it 34 times?
It's 3 to the 4th power. So this was 3 to the negative 4 power. So if we've got the negative, that means we can write it as 1 over just 3 to the 4th and take the negative away.
So if it's not a negative, then it would just be that number.
Yeah, so if it was 3 to the 4th, it would just be 81 on the top there. Yeah.
Okay.
Negative just means we put 1 over that answer. Then we're good.
So how come? Oh, never mind.
Okay. All right, so for the next two, we're not going to graph these next two just because there's a lot of moving around, a lot of different parts and pieces. I mean, I guess we could do a quick sketch if we want to, because again, the quick sketches don't take that long. But next question, let's do this one. Let's do this. Let's do how does f of x equals negative 1/2 times 1/3 to the x power compared to g of x equals 1/3 to the x power. Again, question is, oh, I can't see that. Sorry about that. Barely can see it. So how does f of x equals negative 1/2 to the 1/3 x power? How does that compare to g of x equals 1/3 to the x power? And again, whether it's this one or this one should be the same. Is it growth or decay? Okay, so to figure out the growth or decay, what is our base in either one of these two? What is our base in either one of these two? Base is a third, right? So if the base is and 1/3 is definitely less than 1, right? So if the base is less than 1, that means it's going to be decay. Okay, so we know graph-wise, the graph would have to look something like this because it's decay. Okay, now, so it's saying what did we do to take this graph and get it here? So what transformations, what are we doing to this thing? So first thing is when you have the negative that's here. So if we had 1/3 of the x power, that's the part that's the same. But what does the 1/2 do? Does stretch or shrink?
That's a shrink.
That's a shrink or a compress, right? So they may say compress. They may also say dilation of 1/2. Then what does the negative do? It's a reflection, right? So that means it's reflection. In that case, out here, because it's on the outside, that should be horizontally. So for that part of it, that should be a reflection. Sorry, if it's on the outside, it's vertical. So it should be a reflection across the x-axis. So anything on the outside means it's vertical. And again, if you go up and down, you're jumping across the x-axis. So again, if you had to do just a quick sketch of this graph then, we're going to take this graph we've got, we're going to compress it a little bit, and then we're also going to reflect it, which means that graph would look something kind of like that. Okay, now, and the weird, we'll call it a weird thing, with dilations, if you're moving it around like this, you're not really going to see this compression or this stretching because it's not stacked on top of each other. So this part of when you're compressing or stretching, any type of dilations, you're probably not really going to notice that part. The only thing you can really notice then would be the reflection that we did have it up here. Now we've moved it down here, which means we had that negative out front there.
So reflection doesn't mean you're going through it, just means you're mirroring it.
Mm-hmm. Yeah. Because again, it's a reflection. So like I said, it would be a mirror. So. All right, one more of this one. Again, not going to graph this one. We're just going to name what all happens to it here. Actually, I'm going to run out of room here, so let's go to the next page. Make it so I can actually see it.
Just one more, coach.
Make it so I can actually see it this time.
Just one more.
No promise. Okay, so how does y equals 3 times 4 to the x plus 3 minus 1 compared to 4 to the x power? Okay, so let's get the easy question. What should be the easy question out of the way first? Growth or decay? Yeah. Base is 4, right? Bigger than 1?
Yeah.
Got to be growth.
Oh, okay.
Okay. If base is less than 1, then it's decay. That's a half, if that's a third, that's 0.5, 0.6, anything like that, then we're talking decay. Okay, so again, you got to kind of realize that if we go from 4 to the x power to 4 to the x plus 3, then basically what extra did we add in? We added in an extra 3 in the front. We put in this plus 3 inside here and this minus 1 that's in here. So that's the three things that are going to change this thing. All right, 3 is on the outside. 3 is definitely bigger than 1, so that makes they stretch. Again, they may just say dilation. So stretch, dilation of 3. All right, this plus 3 is on the inside. So that's 3 to the, there we go, 3 to the left. The 1 is on the outside.
So it's down.
There you go, 1 down. So anything in the exponent, that's your left and right movement, opposite direction. Anything outside the exponent, that's your up and down movement. There you go. So again, it's just like when we were doing x squared. Whatever's on the inside, left and right, whatever's on the outside, that's your up and down. The only difference is now it's an exponent and not a parenthesis that we're looking at. I mean, still kind of, it may throw up, in this case, because we're multiplying it by 3, we've got that one. If that 3 stretch dilation wasn't here, it probably would have just been 4 to the x plus 3 minus 1. They probably would have had it written like that, just so you could see that, that 3 was just there because you're multiplying the first part by 3. Okay, so what we're going to do for the last couple of problems, we're just going to, no graphing, no scales, no movement on this one. We're going to just do a couple of things. We're going to identify it as growth or decay. And then we're going to find the y-intercept. And after that, we'll talk about a little bit of money, and then we'll finish this thing up. All right, so for example 1, we're going to do 0.95 to the x power. All right, so the base is 0.95. So is that growth or decay? Got to be decay. Okay, and for the y-intercept, what is 0.95 to the 0 power? Still 1. So y-intercept would be at 0, 1.
Please tell me you're going to have some questions like that on the test.
Absolutely.
Thank you.
Now, somebody may be thinking, so that means every answer for the y-intercept will be at 1. Not necessarily, because again, you may have it like this one, where you can do 4 to the 0 power, which would be 1, but then we're going to subtract 1, we're going to multiply by 3. So the answers may not always necessarily be 1, because again, you may add, subtract, you may multiply, you may do some things to the numbers so that it's not always, it may initially start at 1, but then we're going to move it around as we get through those. All right, so for example 2. Let's do f of x equals 0.5 3 to the x power. Okay, growth or decay?
Growth. Wait, no, decay.
Would the base be that 3 or
Yeah.
0.5?
All right, good question. So the base is at 3.5. So it's got to be the number connected to the x. The 3 is connected to the x. So in that case, your base is 3.
So it's growth.
There you go. So that's growth. Yeah, so base is always connected with the x. The 0.5 is just out there just to throw you off for that part. That's the scale. That's the dilation, if you want to think about it that way.
Wait, so how do you find the y-intercept in the first one?
We plug in x equals 0. So we'll do the same thing for this one. We're going to do 0.5 times 3 to the 0 power.
Which is 0.5 times 1.
Mm-hmm.
So it's 0.5.
So that's 0.5 times 1, which is 0.5. So your y-intercept would be at 0 and then 0.5. So again, just because, and again, if you plug in the 0, initially you do get a 1 for that part, but then because we're going to add it, subtract it, multiply it after that, then it may not always be at 1. It can change through some stuff there. Okay, and then last thing,